Hello, it's Mr. Schrader here, and today I'd like to talk a little bit about objects with uniform circular motion. Here you can see a problem on the screen that we're going to talk about in a minute. And but before we do that, I'd like to talk a little bit about what is uniform circular motion and what have we talked about already with uniform circular motion. So, any object that's moving in a circle or even a portion of a circle is undergoing circular motion and therefore must have some force acting on it, making it move in a circle. Remember Newton's first law that objects at rest want to stay at rest, on objects in motion want to stay in motion in a straight line. They want to maintain that same velocity, and velocity has two parts to it. It has speed and direction. So if you're changing your speed, that means you're an object and you're speeding up or you're slowing down, then you must have a force acting on you. But also, if you're an object that's changing its direction, even if you're not changing your speed, but you're changing your direction, then your velocity is changing. And your velocity won't just randomly change on its own. It's net forces that cause changes in velocity, changes in speed, changes in direction caused by net forces. And lots of different forces can cause net forces. We've seen that and we've studied lots of cases of it. And now I'd like to take a look at this problem. So pause here, go ahead, read the problem to yourself, take a look at this picture, and see if you can wrap your head around what's physically happening. Okay, so here we have an object that's a ball that's tied to a string, and I have got one of these right here, and it makes like this conical pendulum, and I can make this ball go in a horizontal circle like this with this string, and I'm not making it go any faster, and I'm not making it going any slower. I'm just having the ball go in a circle. It's always changing its direction. So why is the ball always changing its direction? There must be some sort of outside force making the ball go in a circle because objects in motion don't want to go in circles. If I were to let go of this string, the ball is not going to go in a circle. It's going to go flying off in a straight line. So let's read what the students have to say about this. Student 1 claims none of the forces exerted on the sphere are in the direction of point C, the center of the circular path. Therefore, I don't see how there can be a centripetal force exerted on the sphere to make it move in a circle. Well, we just said there's got to be some sort of force making it move in a circle because things don't want to move in circles. And the student is just making the claim that, hey, if this is moving in a circle, look, there's nothing in the middle. There's nothing pointing towards the middle of the circle. The string's at an angle. So that's not pointing towards the middle of the circle. And gravity, that points straight down. That's not pointing towards the center of the circle. So if there's nothing pointing towards the center of the circle, there can't be a centripetal force. And we all know that that's false. Now, why is that false? Well, if we make this into a free body diagram, it makes it easy to see that there is something making it accelerate towards the center of the circle. Why don't you pause here and go ahead and draw the forces that are acting on this sphere in the position shown in the figure above. All right, you're back. So I'm going to draw a couple forces here. We got the force of weight, and we got the force of tension. And those are actually the only two forces acting on this object. Let me see if I can make these into arrows. Doesn't like that I put a picture on top of a picture. It says no. We'll just scribble some arrows on there. So hopefully you have a free body diagram that looks like this, where you have tension that's going up and along the string, and you have weight or gravity that's pointing straight down. Now, here we know that the object is accelerating towards the center of a circle. All objects that are turning are accelerating towards the center of some circle. So what force then it acts in that direction? There's got to be something, despite what student 1 says. And indeed there is, especially if we break this tension that's at an angle into its components. So let me get another drawing tool here. And let's put this line going towards the center. And that would be a TX. And let's take a look at a line going straight up. And that would be a TY. I apologize for my drawing tools here, being that this is a screen recording. It's not as well as it would be if this was a live session. So I have two components of tension, and we can see that there is indeed a component of tension, maybe not all of tension, but there's at least a component of tension that is acting towards the center of the circle, and that it's that component of tension, what horizontal component, or TX as we could call it, that is indeed acting towards the center of the circle, causing it to constantly change its direction. Now let's pause here and read student 2's argument, and let's see if we can pick out the flaw in their claim. Okay, welcome back. You think you got it? Student 2 says they see another problem. The tension force exerted by for its vertical component must be less than the weight mg of the sphere. That means that the net force on the sphere has a downward vertical component, and the sphere should move downward as well as moving around the circle. Well, look, I can just prove that false right now. I can make this spin in a circle, and it's not going down. It's going around and around and around, and it's not ever going to fall. I guess the claim for this student is thinking that tensions for some reason must always be equal to weight, that the total tension is equal to weight. And that's not true if we again analyze that same free body diagram. Here, we know the direction of the acceleration is horizontal. It's towards the center of the circle. The acceleration is not vertical. It's not up or down. And if you're not accelerating up or down, well, what can we say about the up forces compared to the down forces? You're right. They're equal. They must cancel each other out. The up force and the down force must cancel. So here, it's not the tension that cancels the weight. It's the y component of the tension that cancels the weight and is the reason why it's held up and not falling. So if we were to write out the algebra for this, I'd make the claim, write true statements that the x component, that's equal to our net force. That's the reason that we're accelerating. But our y component, that is equal to our force of gravity. And that's the reason why we're not falling. If we were tasked with solving for some unknown variable here, we're given m, we're given L, we're given R, we're given theta. So if we were tasked with something like, for example, let's solve for the speed of the ball as it goes around the circle. Well, in that case, we would make it we would substitute in for tx, that tx is t times the sine of theta. See how the x component is on the opposite side of the angle that's provided? And that's got to be equal to your net force, which is mass times acceleration. But hold on, it's a centripetal acceleration. So that means that F net is mv squared over r. Now, this would be very easy for us to solve for the velocity if we were given tension. But we're not given tension. Oh, wait, we kind of are. Ty is t cosine theta. And Fg, we all know, is mass times gravity. So now, given that we have these two true statements, I'm going to draw a line here just to designate the difference between my x statement and my y statement. Given that we have these two true statements here, do you think that you could isolate v? Pause the video now and see if you can take a minute and get v by itself. And in the meantime, also, forget about tension. See if you can eliminate tension at the same time as you isolate v. Okay, welcome back. So here you see that I've already started getting rid of the tension by making a substitution for tension. So if I substitute tension into my x statement, I'm left with mg over the cosine of the angle is equal to mv squared over r, but I also have to multiply by the sine of the angle because it times the sine of the angle. Well, what's sine over cosine? That's tangent. So I got mg tangent theta that's equal to mv squared over r. Notice that the physics of the problem was done a while ago. This is all just algebra. Multiplied by r and square root. So v is equal to g times r times the tangent of the angle and the square root of that. Okay, I hope that you learned a little bit about circular motion and a dynamic situation with a conical pendulum. Please reach out to me and email me with any questions that you have, and we'll see you next time.